How's it going, everyone? Hope you're doing well. Today's video is going to be all about projectile motion. So we're going to be going through a couple different scenarios involving motion, and we are going to try and solve for specific information in each scenario. In our first diagram here, we have a dog kicking a soccer ball, and this is basically just based off of those old movies with dogs playing different sports. I remember watching Air Bud, which was about basketball. But let's say this little guy is called Banjo, and he is a star soccer player. So we can see from the diagram that Banjo has kicked the soccer ball at a 40-degree angle with the horizontal, and it's got a speed of 30 meters per second. So what's really interesting about projectile motion questions is just from this information here, we can actually solve for quite a lot. So the first thing we want to do is we want to look at the ball's maximum height. So the target or the trajectory of the ball here looks kind of like a quadratic. And so we have a max height that the ball reaches before it starts to come down to the ground. The first and probably most important thing we need to do is we need to remember that velocity is a vector. So if we look back at the ball, the speed of the ball is 30 meters per second, but the fact that we have an angle associated with that movement tells us that we have a vector. So our vector would be 30 meters per second. And I could say that this is east 40 degrees north. And that's just saying that we're starting looking horizontally, and then we're moving 40 degrees upwards. So, okay, we have a vector. The problem is, when we're working in 2D, and this is a 2D problem because we are moving both horizontally and vertically, we need to consider what's called the components of a vector. So if I were to draw out the velocity here, just as a right angle triangle, so this has a value of 30, and then our angle down here is 40 degrees. So this vector in 2 dimensions can actually be broken down into its horizontal component and its vertical component. So that just means that it has a horizontal velocity and a vertical velocity. And when we combine those two, we get our total value for our vector. And the way we're going to solve for these individual components of velocity is with our trigonometric ratios. If I look at cosine for 40 degrees, I could say that cosine 40 is equal to the adjacent side of the triangle over the hypotenuse. The adjacent side happens to be x, and then our hypotenuse has a value of 30. And if I were to isolate for x, I could say that it has this value, which if we plug into our calculator, will give us something like 22.98 meters per second. So that is the velocity just looking horizontally. If we want our vertical velocity, we are going to have to use the sine ratio, because if I set up sine 40 degrees, the ratio is going to include the opposite side of the triangle, which is y, over the hypotenuse. And once again, I can isolate for y. And my value will roughly be 19.28 meters per second. So just from this angle, we can say that we now know the horizontal velocity is 22.98, and our vertical velocity is 19.28. And I'm just going to erase these arrows here so it's not confusing. Okay. The thing is, in these kinds of questions, we can assume that there's no air resistance or friction. However, we cannot ignore acceleration. What that means is this 22.98 meters per second to the right or east is going to be constant because there is no force opposing that motion. But in the vertical direction, we do have the force of gravity, and for our purposes in physics, we're going to use the value of negative 9.8 meters per second squared. That is the acceleration, the value of acceleration, and we put a negative because it's usually opposing motion, meaning the ball in this situation is moving upwards, acceleration is moving downwards. We want to highlight that with a negative value. Okay, this is a good start, but now we need some sort of equation to help us figure out what this max height is over here. I can say for certain that when the ball reaches its max height, it definitely has a horizontal velocity of 0 meters per second, right? If I throw something in the air and then it reaches its max height, at that apex of its motion or of its trajectory, it's going to have a vertical velocity of 0. And with this information, we just need to pick the appropriate kinematics equation. So these are the core kinematics equations. I'm pretty sure you'll have these on any sort of physics test, so don't worry too much about memorizing them, but it is super useful to practice them and to get comfortable using them. The first two aren't too bad. If we were to look at this one here, it's really just a rearranged version of the V equals delta D over delta T, and this just relates velocity with displacement in time. So hopefully you're familiar with this one. And then this one down here is fairly similar. It's just showing the same thing, but with acceleration, because we know that acceleration is the total change in velocity over the total change, or the total passage of time, I should say. The other ones are a bit more complicated. They take a little bit more work to prove, but you don't have to worry about the proofs. You just have to understand how each equation can be useful depending on the situation. So if I just circle back to the diagram, I'm looking for max height. So I need something with displacement, right? I need to be solving for displacement. And I have my initial vertical velocity, my final vertical velocity, and acceleration. And looking at my equations, it looks like I'm going to go with this one right here, because I have all of the variables except for displacement. So let's just go back here so I have some space to write things out. Vf squared, well, our final velocity is a 0, so we can just say that's a 0. This will be our initial velocity of 19.28. And then just making sure that our acceleration is negative to show that it's in the opposite direction. So if I square 19.28, I get this. 2 times negative 9.8 will be negative 19.6, and 0 squared will just be a 0. So now I just need to move this over. And divide both sides by 19.6. And it looks like our total displacement was 18.97 meters. And that is the answer to our first question. That tells us that this max height here is 18.97 meters. All right, that's the first one done. Let's check the second question. How far did the ball travel horizontally? Well, we already know the horizontal velocity of 22.98 meters per second, but we don't actually know how long the ball was traveling at this speed for, or at this velocity. So what we're going to need to do is calculate how long the ball was in the air and then multiply our horizontal velocity by that amount of time. And I'll show you how I'm going to do that. Let's look back at our kinematics equations. And immediately I look at this one. Whoops, let's try that again. Because once again, I already have VF and VI, which is final velocity and initial velocity. And I also have acceleration. So I can solve for how long the ball is in the air. And here's how I'm going to do that. Just going to give myself more space again here. If I were to think about what VF is going to be, I have a couple of options. I could either stick with the fact that at the ball's apex, it's going to have a vertical velocity of 0. So let's try that. Final velocity will be 0. Initial was this. And then we just have our negative acceleration. So I'm going to move this over. And then divide out both sides by 9.8. And we get a time value of approximately 1.97 seconds. Now, that would only be the time that it takes for the ball to rise up and reach its max height. So what we need to do is actually multiply this value by 2 to get the total time of the ball in the air. So that's going to give me 3.94 seconds. Another way I could solve for time is I could think of it this way. Instead of using 0 as my final vertical height, I could just say, okay, if the ball is being shot upwards with a value of 19.28 meters per second, once it ends up hitting the ground, it's just going to have the same magnitude, just in the opposite direction, right? Because there's no other forces at play here. So if there's only acceleration working, we're going to have the same speed. And I'll show you that we'll actually get the same value. So instead of a 0 as my final velocity, I'm just going to set it as a negative 19.28 to show that it's in the opposite direction. Move this over. We're going to need to add these together, or I guess technically subtract them. So we've got this. And then finally, we can solve for time. And we get pretty much the same value, just slightly off because of rounding. And now that we have time, we can just multiply our vertical velocity by that amount. So 22.98 meters per second times 3.94 seconds gives us a total horizontal distance of about 90.5 meters. So that is our second question complete. So let's just do a quick overview of the key concepts here. We learned that velocity is a vector, and it can be broken down into its horizontal component and vertical component. We can probably ignore air resistance or any kind of friction unless otherwise stated in the question. Gravity is going to provide a constant downward acceleration, and we're going to represent that with a value of negative 9.8 meters per second squared. And finally, as seen in our kinematics equations, distance, time, velocity, and acceleration are all related. Okay, let's try one more scenario where we're solving for something different. And now we are entering the world of Pokemon, because that was definitely one of my favorite cartoons growing up. Here we have Ash, the main character, throwing a Pokeball over a tree, trying to capture a Venusaur. And I did actually look this up. Venusaur has an official height of 2 meters. So Venusaur has the same height as Ash, which is not very realistic because Ash is 10 years old, but let's use our imagination for this scenario. And the question that we're asked here is, will the Pokeball clear the tree? So Ash is throwing the ball with this trajectory, but we want to know, is this ball, the Pokeball, going to be able to pass over this 6 meter tall tree that is 25 meters away from him? So we're looking for slightly different information here. We don't really care about the max values. What we actually want to do is figure out how high the Pokeball is at this point, 25 meters away from Ash. Okay, so our first order of business is just like with the first scenario. I want to break down my vector into its components. So I'm just drawing out the right angle triangle to solve for horizontal and vertical velocity. Just to speed things up here, based on the first question, we know that the horizontal velocity would be 20 cosine 30 degrees, and the vertical velocity would be 20 sine 30 degrees. And so these values are going to be 17.32 meters per second this way, and exactly 10 meters per second this way. All right, that's definitely super helpful. But because we're not solving for any max values, I can't assume that our vertical velocity ends up being 0 in this situation, because I don't know for certain that 25 meters away from Ash, the ball is at its max height here. What I can do is figure out how long it takes the ball to reach that point. And I'm going to use the horizontal velocity this time. We're just going to need our basic v delta d delta t equation. Because I know the velocity is 17.32 meters, and based on the fact that we can ignore resistance, this horizontal velocity is constant. It's gone 25 meters, and we just want to know how long it took that to happen. So if I rearrange things to solve for time, it's going to look something like this. And that value is about 1.45 seconds. So now we know that it took the ball 1.45 seconds to reach this point. What we need to do now is use this value in the vertical direction to see what the vertical height of the Pokeball will be. Let's go back up here and see if we can pick the right equation for the job. We have VI because we solved for it. That's 10 meters per second upwards. We don't have VF, but that's not a problem. We definitely have acceleration. And now we actually have time. So we have 1.45 seconds. And we are solving for displacement. And just scanning through our equations, the best equation is going to be this one down here, because I have all of my values except for displacement. So let's plug those in. And then here we just have to be careful that we are following bed mass. So we want to square our value first here, and then start multiplying everything together. And just continuing to multiply things together here. We can see that we have a displacement of about 4.2 meters. So if I scroll back down here, I could put 4.2 meters as my value for the vertical displacement that's occurred 25 meters away from ash, which is exactly where the tree is located. Now you might think, okay, 6 meters is larger than 4.2 meters, so clearly the pokeball was not able to clear the tree. However, we have to consider what the starting height of the ball was, right? Because the ball was not thrown directly from the ground. It was thrown 2 meters up. So what I need to actually do is add this vertical height to my answer to get an accurate height relative to the ground. So 4.2 plus 2 would be 6.2 meters. And now we can actually see that the pokeball would in fact clear the tree. So just once more to re-emphasize the point, this 4.2 meters is basically the ball's height relative from where it was thrown. So this would be 4.2 meters, but then I can't forget to add the extra 2 meters down here. Okay, that is going to be it for today. We did cover quite a bit, and hopefully you're feeling a bit more comfortable with looking at these kinematics equations and being able to determine which one is the best for any given situation. Thanks for watching, and happy studying.